Hello and welcome to the Spartan Student version 9 tutorial series. Today we're going to be going through our first tutorial, which is called Walking Through Spartan Student. So we're going to get started by launching the program. And once you've got the program opened, the first place you'll want to go is the Activities menu here at the top right. So click that menu and then click this Tutorials entry. And you'll see our list of 11 tutorials here. Go ahead and click on the first tutorial, Walking Through Spartan, and you will open the tutorial PDF. I've already got it open here in another window. I'm just going to bring it on screen for you quickly. Alright, so here's our PDF. You'll see Tutorial 1, Walking Through Spartan Student. And at the bottom of this first page, you'll notice a set of instructions for navigating to the tutorials directory, whether you're on Mac or Windows operating system. So for the Mac OS, this will be found on the disk image that you downloaded from our website. And for Windows, I'm going to go ahead and show you how to get there now. So I'm going to head back into our full screen and then click this Open an Existing Document button. And to navigate to our tutorials directory, we will go to our C drive, to our Program Files folder, then to the Wavefunction folder, the Spartan Student 9 folder, and finally our Tutorials folder, and there is our file here. So I'm going to click to open it, and just to show you, this is the path once again to get to the tutorials directory. Alright, so we're going to open that, and we're looking at an ethane molecule. So just going to start with some general operating features in Spartan Student 9. So we'll start with rotating. If you click with the left mouse button and hold your button down and then drag your cursor, you can rotate your molecule. So you can see I'm rotating it up and down and left and right now. You can do this in 360 degrees. Now if I wanted to use the left mouse button and perform the same operation, we could translate the molecule. So now I've clicked with the right mouse button and I'm holding down now, and we can drag up to translate, or left or right, down, diagonal in the XY axis. Okay. We can zoom in and out by scrolling up or down. Alternatively, you could hold the Shift key and then click and drag with the right mouse button up to zoom in, down to zoom out. And then last thing I'll quickly show you is if you hold the Shift key and use the left mouse button and click and drag, you can rotate your molecule in plane. So you can see we're rotating by dragging down, we're rotating counterclockwise, and up, we're rotating clockwise. Alright. Lastly, I'm just going to show you, if you go to the Help menu at the top right corner of your screen, and then click this first entry, Spartan Student version 9 Help, and click this General Operating Features entry, you'll see that we have a set of all of the operations you can perform with the mouse and keyboard in Spartan Student. Alright, so moving on, we're going to take a look at the model menu. So we're going to start by taking a look at the wire model. So I'm going to head to the model menu here between edit and geometry. Then I'm going to click wire. Alright, just zooming in, so you'll see we've got a conventional line formula here, and then we've got our different atoms represented with different colors. So we've got these white regions for hydrogen and these graphite colored regions for carbon. So the wire model uses 1, 2, and 3 lines between atoms to indicate single, double, and triple bonds respectively. We've only got single bonds here, but if, let's say, these two carbons were double bonded, then we would see a second line connecting them. Alright, so we're going to move on to the ball and wire model, which is identical to the wire model, except that the atom positions are represented by these colored spheres. We've got the graphite color for carbon and the white color for hydrogen, just keeping with our color conventions. And next we can move on to the tube model. So the tube model is also identical to the wire model, except that the bonds are represented as solid cylinders. So this will do a better job than the wire model at conveying three-dimensional shape. And you'll see we've still got the color conventions going on here to designate different atoms. So the white region's hydrogen, the graphite region's carbon. And we can move on to our default model, this classic ball and spoke model, which is an iteration of the tube model. So just like we added spheres to represent the atoms' positions on the ball and wire model, we've added these colored spheres to the tube model to represent the atoms' locations as well. Alright, so lastly, I will give you a quick look at a space filling model, which is quite different from the other four, in that there are no bonds shown, which you may have already noticed. So each atom is actually displayed as a colored sphere, which is representative of its approximate size. And so this is representing or giving a measure of molecular size. While there aren't any lines between the atoms representing bonds, we are meant to infer the existence or the absence of bonds by the extent to which these spheres of neighboring atoms are overlapping. So we've got this carbon, and we'll see that they're overlapping, which is indicating a single bond there. And the same can be said for the hydrogen spheres here overlapping with the carbon, or over here. Alright, so we're going to switch back to our classic and default ball and spoke model, and then we are going to move on to our next molecule, which will be an acetic acid dimer structure. So at the bottom left of the screen, I'm just going to click this right arrow to move on to acetic acid dimer. Now, alternatively, you could use this slider. You can click and hold and then drag to step through our molecules. And you may have already noticed that at the bottom of the screen here, you'll see the name of the molecule populated. Now, this is not an automatic naming feature. This is actually indicating that we have a database entry for this acetic acid dimer structure. So we've run this calculation on this structure, and we've got a bunch of data. So we've got energy data, IR, and NMR spectra data, and an assortment of atomic and molecular properties all included in our database, the SSPD, which stands for the Spartan Spectra and Properties Database. Alright, so taking a look at this acetic acid dimer structure now, if we head into the model menu, you'll notice that separate from the models that are available, we have these toggles. So if I were to toggle the hydrogen bonds off, you'll see those dotted yellow lines between our hydrogen and oxygen atoms disappear. And I can toggle the hydrogen bond indicators back on using that toggle. Alright, moving on, we are going to take a look at propene, and we're going to head to our next menu, the geometry menu, and we're going to use this first tool, the measure distance tool. So I've clicked that tool, and you'll see at the bottom left it says select select two atoms or a bond. If you select two atoms, then you'll see at the bottom right the distance between them is reported in angstroms. Alternatively, you could select the bond between them, and that would report the same distance. The length of the bond is 1.5 angstroms. And you'll notice that double bonds are, of course, shorter than single bonds. We've got 1.33 angstroms there, and you could get the same value from measuring the distance between these two atoms. And you could measure the distance between a carbon and any of these hydrogens it's bonded to. You can actually measure the distance between any two atoms, so they don't actually have to be bonded. If I were to select this hydrogen back here and this hydrogen up here, we could get the distance between them as well. We've got that 3.54 angstroms reported. Alright, so I am going to click this View button to exit our Measure Distance tool, and then I'm going to click over to our next molecule, ammonia, and we are going to head back into the geometry menu and move on to our next tool, the Measure Angle tool. Alright, so our Measure Angle tool, we can select either 3 atoms or 2 bonds. So I'm going to show you both here. We can select the hydrogen, nitrogen, and hydrogen. And you'll see we've got this 106.36 degree angle between these atoms. If I were to click on this bond, you'll see that the 2 atoms connected to the bond are highlighted. And if I click on this bond, then it'll highlight that last atom, and we'll get the same number reported down here. Alright, so I'm going to click that View button again and move on to our next molecule, which is hydrogen peroxide. And for this molecule, we'll head back to the geometry menu, and we're going to use the third tool, the Measure Dihedral tool, to measure this dihedral angle. So I'm going to click hydrogen, oxygen, oxygen, and hydrogen in that order, and you'll see we've got our dihedral angle measured. And alternatively, we could click on these 3 bonds and get the same value. Alright, so we're going to move on, and I'm going to click View and click to our next molecule, acetic acid. Now for acetic acid, we're going to take a look at the properties panel. So we can either click this properties icon or go to display properties, and that'll open this molecule properties panel. You'll see we have the molecule tab selected at first. So from this tab, we'll get some information like the name, formula, some different energy values, and the weight, mass, and some different heat values, as well as our dipole moment, and we can display this dipole vector as well. So I'm going to check that box, and you'll see we've got our dipole vector arrow has appeared, and I can uncheck it to remove that. Next, we will step over to the QSAR tab, and that stands for Quantitative Structure Activity Relationship. So that'll give us some information on the area, volume, polar surface area, ovality. We've got some information that was computed from electron density, such as the min and max on an electrostatic potential from the electron density surface here. We've got log P, polarizability, hydrogen bond donor and acceptor counts, and there's some other info in there as well. Alright, so we'll move on to the thermodynamics tab. So we've got our 0-point energy, we've got our entropy, enthalpy, Gibbs free energy, and then our heat capacity at a constant volume in this tab. We can click over to our 2D drawing tab, which will give you a 2D representation of your structure. And most of the operations that you can perform in 3D are available in 2D, so you could zoom in on this by scrolling up, which I'm doing now. You can translate it using the right mouse button and dragging, or you can rotate it in plane by holding shift and dragging the left mouse button after clicking like so. Alright, so we're going to step into the Utilities tab, and so in the Utilities tab, we've got some specialized functions here involving bonding, labels, structure, and bonding and chirality. So for example, if you change the absolute configuration, you will convert your structure to its enantiomer, and we've got some other tools in here as well. Alright, so from within this molecule properties panel, as long as you've got this panel on screen, regardless of what tab you're in, if you click on an atom, you'll actually open a new panel, which is the atom properties panel. So I'm going to go ahead and click this carbon atom, and just translate this over a bit, you'll see we've got the electrostatic charge as well as the chemical shift that was calculated here. So that's a 13C NMR shift. We've got the name, symbol, and atomic number, the mass number, which you could switch if you wanted to look at a different isotope of carbon, and the same holds true for any of these other atoms. So if I were to click on the oxygen, we could get the same information as well as have the ability to change the isotope, and the same is true for hydrogen. We've actually named our isotopes here, deuterium and tritium. So if you wanted to take a look at, for example, a form of acetic acid where all of the hydrogens were actually deuteriums, you could replace all of these with the 2 mass number, the deuterium isotope. Alright, so that's going to do it for that atom properties and the molecule properties panel. Next thing we're going to do is step to our next molecule and take a look at its calculated infrared spectra. So I'm going to click on that arrow, and we've got water here. And I'm going to click this spectra panel, which you can also navigate to from display spectra. So from within this spectra panel, we're going to click on this green plus icon to add our calculated infrared spectrum. Alright, so we see this spectra populates with these 3 peaks. You can click on these peaks to show the vibrational mode at that peak. So for example, here at 3728 inverse centimeters, we have this asymmetric stretch going on. On another peak, we would have a different vibrational mode. So if I click this peak, then you'll see we've got a symmetric stretch. Or this peak, if I can select the bend vibrational mode. Now, if you have any trouble clicking on these peaks, you can always add the table by clicking this tables icon on the left, and then view your peaks as these different checkboxes. So we've got our vibrations in inverse centimeters in the left column, and then the intensity in the right column, and you'll see that our largest peak corresponds with this 1 intensity here. Alright, so you can actually zoom in on this spectrum plot. If you wanted to use your scroll wheel, you can zoom like so, and you can reset your zoom by clicking this cancel zoom icon, the X on the magnifying glass, to reset to where you started. So I am going to click this eraser icon to delete this spectrum plot, and then I am going to tab over to our next molecule by clicking the arrow, and we've got a cyclohexanone molecule. So we're going to take a look at this infrared spectrum plot. So you see we've got a lot more going on here. There are many more peaks, and I can drag my cursor to these to highlight them, or I can click on the peak to view it, as well as use this tables to click through them there. Now I'm going to add, by clicking this green plus icon, the experimental infrared data. So we're going to pull this in from the public NIST database, and you'll see there's a pretty good correlation between these plots, although it's not a perfect match. If you wanted to zoom in and take a look at where these deviate, you could do so by using your scroll wheel and reset your zoom again with that cancel zoom button. Alright, so I am going to erase this plot, and then we're going to move on to our next molecule, which will be camphor. Just going to rotate this a touch so you can see all of our carbons on screen, because we're going to be looking at the NMR spectrum. So we're going to add this 13C calculated spectrum. And so if you click on any of these peaks, you'll see on screen that a little red C target icon appears around it. So that is indicating that this 57.5 shift corresponds with this carbon, and we could do the same for these other peaks to see where they correspond on the structure. And if you wanted to click on a specific atom, for example, we'll see here the 11.6 shift reported for this carbon. If I were to click out into the 3D space and exit this spectra by clicking View, and then clicking this carbon atom and opening the Properties panel, we can take a look and see that this matches here. So we've got the chemical shift reported on this atom, and the same shift is reported here. Now, you can see here we've got experimental shift data being reported. So that's coming from the NMR shift database online. And if I were to click this plus icon and add the experimental shifts, then we could see those here as well. So we've got 11.6 or 9.2 here, which corresponds, if I were to click View and then click this atom, with the experimental shift 9.2 there. Alright, so we are going to move on from the 13C NMR shifts, and we're going to take a look at our proton spectrums. So first one we're going to look at is an idealized proton spectrum, where the 3-bond hydrogen coupling constants are set to 0, which will be this one here. So each one of these shifts will again highlight the corresponding atom on the structure, and these triple peaks actually correspond with these methyl hydrogens, so they have identical shifts, and therefore all three will be highlighted when you click on that shift. Now, if we wanted to move on to take a look at how this matches with experimental, we could pull that in and visualize that data. Or we could look at a traditional calculated proton spectrum, where you'll see the coupling constants and the splitting that goes on here. So I'm just zooming in, and I'm going to drag across so you can see what goes on there. Alright, and I'm going to reset this zoom and just show you again that these triple peaks will correspond with our methyl hydrogens, as you can see on the screen above here. Alright, so we're going to move on from NMR spectra and move on to a new molecule, this 3-benzoyl aniline molecule. And we're going to take a look at a feature that is actually new to Spartan Student 9, which is the UV visible spectrum. So we can add this calculated UV vis plot, and you'll see our curve here. If we wanted to add this table, we could see that the first 6 excited states were calculated, and you can see these wavelengths and intensities. We've got our lambda max here at about 227 nanometers. And we could go ahead and add from the NIST database this calculated, this experimental UV vis spectrum. So you'll see this plot is populated as well. Now, to note the differences between these, while the calculated UV vis is going to be the least accurate of the available spectra in Spartan Student 9, it's not going to be sufficient to accurately identify a molecule's color. The underlying models are good enough to tell you whether a substitution at a particular location or some other subtle structural change will result in the overall color shifting more red or more blue on the UV visible spectrum. Alright, so that is going to do it for the spectra panel. I'm going to move on, delete this plot. I'm going to click View, and then I'm going to exit this panel, zoom out a touch, and move on to our next molecule, ethylene. And we're going to take a look at the orbital energies surfaces. So I'm going to this orbital energies icon. You can also get there from display orbital energies, and you'll see that this line, this axis kind of appears on the left of your screen, and we've got a range in electron volts here, going -25 up to 10, and then you'll see we've got two labeled orbitals here. We've got our HOMO, the highest occupied molecular orbital, and our LUMO, our lowest unoccupied orbital. So let's go ahead and click on the LUMO, and we've got this surface that appears here. You'll see it's got a 2.6 electron volt measure on this orbital energy plot, and if we wanted to change the style of this model, we could do so from the bottom right style drop down menu here. So if I were to click mesh, you could see here the space inside of our surfaces. And just quickly going to show you some other orbitals. So we can go one above the LUMO here, we could go down to the HOMO here, or to one below the HOMO there, and several below the HOMO down here as well. Okay, so we are going to move on from the orbital energies and take a look at some other surfaces. So I'm going to click View to exit that orbital energies tool, and then I'm going to click the arrow at the bottom left to step over to benzene. And for benzene, we're going to take a look at the electrostatic potential map. So I'm going to click this surfaces icon, and we've already made this electrostatic potential map available for you here. So you'll check this box, and you'll see that we've got this nice surface that appears on our benzene. So I'm going to click on our surface, and then I'm going to right click and click properties, and you'll see we've got this property range up at the top in kilojoules here. So we've got -97.8 down at our lowest in red, and then 72.25-ish as our blue, our max. So if I were to click on any of these spots on our surface, this electron density surface, then you'll see the value reported here. So in this green area, I'm at about -27 kilojoules. And if I were to click in the red area, you'd see we're very close to the minimum, or in the blue area that we're approaching the maximum. Just like with the orbital energies, you can change the style of this. So we've already seen mesh. That's what the mesh style looks like with an electrostatic potential map. And we could change this to dots or to transparent if you wanted to see that structure underneath, or back to solid if you just wanted to look at the surface itself. Now if I were to add a legend here from the display checkboxes, you'll see this key, this legend, appears on the left, and just like when I had the value here changing from clicking on different regions, you'll see that the legend does the same function. Okay, so just to mention, the positive regions are going to be around our hydrogens. Let me switch this to transparent so you can see that. These positive regions are going to correspond with our hydrogens, and then these negative regions are going to correspond with our pi orbitals. Alright, so we're going to move on to our next molecule, which will be aniline, and then we are going to take a look at a local ionization potential map for aniline. Alright, so I am going to right click click Properties, and I'm going to switch this to the mesh style so you can see through the surface and see the aniline structure underneath. Now, on the local ionization potential map, we have these regions of red and regions of blue, and this is a property range in electron volts. So what we're reporting here is a surface that will tell you where the removal of electrons is easiest and most difficult. So we've got our regions in blue where it would be the easiest around this nitrogen, for example, and in red, which you can see corresponds on the ortho and para carbons of the benzene ring. Okay, so last molecule we're going to look at today is cyclohexanone, and we're going to take a look at a LUMO map here. So just like when we looked at the orbital energy surfaces before, you can add a orbital energy surface from the surfaces panel, and this is where our LUMO is in these regions. If I were to switch to this absolute LUMO map, you'll see that the map essentially answers the question, if a nucleophile were to attack, where would the electrons go? So the map is going to map the colors of the electron density surface with the orbital information that you'll get from this LUMO. So the blue spots displayed on the map are going to indicate regions where locations for where addition can happen, and you can see sites for possible regiochemistry going on there, comparing which sites are preferred. So just again, we've got our LUMO here, and you can see these regions of the cyclohexanone structure, and switching to the map, you'll see them here. Alright, so that is going to do it for our very first tutorial. Next time we're going to move on to our second tutorial, which is all about building molecules in 3D, and I will see you then.